Please open to page 132 in your student journal. In a previous class, we worked in groups to solve 3 different application, aka word problems, and each group came up with its own strategy of how to approach those problems. Some groups did guess and check, some groups drew pictures, some groups made a table. There was a wide variety of options that I saw. Today we're going to start learning how we can solve those types of problems a little more efficiently and hopefully be a little less time consuming too. So if we take a look at exploration 1, it says your family opens a bed and breakfast. They spend $600 preparing a bedroom to rent. The cost to your family for food and utilities is $15 per night. They charge $75 per night to rent the bedroom. So let's take a look at how we could write an equation for each piece of this problem. So we have the cost equals $15 per night, so $15 times the number of nights, plus the $600 they spent to fix up the room. If we write an equation for revenue, aka their income, how much money they're going to make off that room, the revenue equals $75 times the number of nights that the person stays. In letter C, it says a set of 2 or more linear equations is called a system. So what we can do is we can take our 2 equations and we can write them as a system of equations. I know some of you, when you worked in your groups in that previous class, you tried writing equations but you got a little stuck because we were used to just having to write 1 equation to solve a problem. But now the types of problems we're looking at that we explored in that previous class in our groups, we need more than 1 equation. So just something for us to think about. Now when it comes to solving those, we could, in some groups, when we worked on those 3 problems, some groups did make a table of values, and we can do that here. How we make that table of values is we substitute in those different values for x, and we worked on creating those tables in a previous unit last trimester. So if we have 0 nights, our first equation, our C equation, we'd put a 0 in for the 15. And we'd have just $600. For the revenue equation, if we put a 0 in for x, we end up with just a 0. So if we continue that, so if we replace the 0 with a 1 now for the x, we have 15 times 1 is 15 plus 600. 75 times 1 is 75. So that idea of substituting values for x to get out our value for dollars for cost or revenue, that's an idea that should be pretty familiar to us. I'll do one more and then I'm going to go ahead, just for the sake of time, I'm going to go ahead and fill in the rest of the table for us. So if I substitute a 2 in for x, 2 times 15 is 30 plus 600. 72 times 5 is 150. We could also, instead of continually substituting in, some of you caught on to this when we made tables in a previous unit, we're just adding 15 to that cost row each time. So if I just keep adding 15, that's the pattern, I can make pretty quick work of this table. And that could be something you just keep in your calculator and you just keep hitting plus 15. In the bottom, we're just adding 75 each time. So if I just keep adding 75, and again, you can just keep hitting plus 75 in your calculator, I once again can make pretty quick work of this table. So what we're looking for, it says we want to Determine how many nights your family needs to rent the bedroom before recovering the cost of preparing it. So in other words, they want to find that break-even point. So where will the cost equal the revenue? So they want to know how many nights are they going to have to rent this room out before their repairs pay off, essentially. So where's that break-even point? So if we take a look through our table, we want to find where cost equals revenue, and we can do that when our X value is 10. So we can do that for 10 nights. So if you look on the next page, Exploration 2 continues, and it says, how many nights did your family need to rent the bedroom before breaking even? And we just discovered that that is 10 nights. Now I know some of you are thinking, Miss Golly, we need a faster way to solve these problems. Making that table, that took quite a while. Writing the equations was pretty quick though. But making the table, that could take a while. What if it wasn't until 20 nights and we had to take it all the way out to that? So let's try, we made a table. Let's try graphing our equations and let's see what happens. So if I graph, I'm going to start by graphing the cost one. I'm going to start by graphing the cost one. And one of the easiest ways to graph is we can just pull some ordered pairs right from our table. So we have, when we had 0 nights, we had $600. And then I'm looking for this scale along the y-axis goes up by 75s. So I'm going to see if I can find some of those numbers in my row for cost. So 675, I do find that when x is 5. So x is 5, y is 675. And then 750, when x is 10, we have a total of 750. So this is my cost equation graphed. And again, I just pulled the values that are highlighted in red up on the table. Those are the 3 points I chose just based on that scale on the y-axis. That's the reason I chose those. Now with the revenue one, with the revenue equation, grab a different color, I'll do that one in blue. With the revenue equation, we could do slope-intercept form because our slope is 75, and that's conveniently what that y-axis scale goes up by. Remember, we could really add a 0 on there, and that would be our y-intercept. So y-intercept of 0, and then we just go up 75 over 1 each time. In 75, I know you're thinking, Miss Golly, but we're not counting up 75 boxes. You're right, because one box when we go up counts as 75. One box as we go up counts as 75. So I know you're thinking, Miss Golly, yeah, I see from the table, I see our break-even point, but now how do we get that from the graph? Our break-even point was 10 nights at $750. So here's our 10 nights. And if we take a look, both of our equations, 10 nights, $75, or $750, excuse me. It's the ordered pair on the graph where those two equations meet. So you could make out a whole entire table of ordered pairs and figure out that break-even point, or in other words, where are the two equations the same or equal. And then we also discovered if we graph them, the place where they intersect is also where the two equations are equal. So if we have the intersection point, we can fill that in part D. Found the intersection point. What does that intersection point represent? We just talked about that. This is our break-even point. It's our break-even point. It's the same as it was in the table. It's the same from the table. So where our numbers matched up in the table, our 10 nights, $750, is the same place where our two graphs intersect. So how could we solve a system of linear equations? Remember, linear equations, we have two or more equations. How can we solve those by graphing? So we could, so how can you solve them? And we're going to, it's nice and written out for us, if we go to page 134, Core Concepts, it's already nice and laid out there for us. So page 134, let's go ahead and turn to that page. It's just the next page. And it's laid out for us in the Core Concepts. Step number 1, graph each equation in the same coordinate plane. That's what we just did. Estimate the point of intersection. We found that to be 10, 750. And then it says we can check by substituting in for x and y in the original system. The check part we didn't really show in that exploration. So I want to go ahead and I want to kind of walk you through your practice and show you one full problem of what this looks like. So let's go ahead and turn to page 136 in your student journal. And we're just going to try out the first problem on this page, which is question number 10. It says solve the system of linear equations by graphing. Step number 1, we need to graph both equations in the same coordinate plane. These two in question 10, they're conveniently in slope-intercept form for us. So for our top equation, and again, you need to write things out, go ahead. Our slope is -1. Our y-intercept is 3. So we start on the y-axis, go up 3. Here's where we start. Now a slope of -1, we have a couple choices. We can go down and right. And since we're looking for an intersection point, when I graph that first equation, I want to graph as many points as will fit on my graph. So down and right, or up and left. You also want to make sure when you're graphing these, I can't do this on my screen, but you can on your paper. Make sure you use a straight edge so we find that intersection point. For the second one, I'm going to go ahead and grab a different color here. For our second equation, our slope is really 1. There's really a 1 in front of each of these x's, a -1 and a 1. Our y-intercept is at 5. Always start at the y-intercept, up, 1, 2, 3, 4, 5, there it is. And now a slope of 1. I could go up and right, but when I go up and right, I'm not getting anywhere near that blue line, so I'm going to need to go down and left, down and left. As soon as your two lines intersect, you can stop drawing points and go ahead and use your straight edge and draw your line. Now, graphing the two equations, we're not finished. We're not finished. We need to find where the two equations would be equal. The two equations will be equal where the two lines intersect. That is the ordered pair -1, 4. Now we also need to make sure, step 3 is that we check. That's a great thing. Whenever we solve equations, we can check our solutions. In order to do that, we need to substitute our solution into each equation. You might need to label the x and y values from the ordered pair so you substitute incorrectly. So, our first equation is y equals -x plus 3. That's the first equation in number 10. So in for the y, I'm going to substitute the 4 from our ordered pair, and in for x, I'm going to substitute -1. Then x is already negative in the equation, so when I put in -1, that's going to turn that value positive for us. We get 4 equals 4, the first equation checks. You need to make sure you check the second equation also. So y equals x plus 5. 4 again goes in for y, -1 in for x. 4 equals 4, the equation checks, the solution checks in both equations. How did I know y was 4? Again, it's from my intersection point. The y value was 4, the x was -1. Let me just have you take a look at the other sections of the assignment. In the first section, all you're doing is substituting the ordered pair in to each equation and seeing if it makes the system true. So does the ordered pair work in both equations? If it works in both, if it makes both equal, it's a solution. They will not all be solutions. In the next section, 7 through 9, you have to first of all pick out the ordered pair of the intersection point, then check your solution. Your assignment can be found in your calendar, but what you need to do today is go over to the shelves, pick up a progress check for 5.1, and do your best on it. You can use your notes on it, but please try it on your own. When you're finished, check your progress check, and then show your progress check to me. If you're stuck on your progress check, please ask me questions. I don't expect that this little video doing a couple examples that you're going to be ready to rock and roll on every single question. So let me know what I can help you with, please.